Good morning, everyone. My name is Najha Anissa. Metric number BC250876 will be a first presenter to present about solving family-based problem using partial differentiation and multiple integral. In this presentation, we will show how mathematical method can help solve everyday family problems from a physicist perspective. Many families today face two common challenges at home. The first challenge is high electricity bill caused by the frequency use of air conditioner. And the second challenge is excessive heat entering the house to the roof, making the indoor environment uncomfortable. Although this may seem like ordinary household issues, they involve physical phenomena such as heat transfer and energy consumption. As a physicist, instead of making assumptions, we use mathematical models to analyze this problem quantitatively and identify the most effective solutions. In this project, we use two mathematical techniques, which is partial differentiation and multiple integral. Partial differentiation is used to determine which factor has the greatest influence on electricity consumption, while multiple integrals are used to calculate the total amount of heat entering the house through the roof. This mathematical method allows us to make evidence-based recommendations that can help family reduce energy consumption and improve home comfort. Now, let's begin with our first problem, which is optimizing home air condition energy consumption by presenter 2.
Next, we will be moving on to our first problem's questions, which is to managing winter heat loss to save on family heating bills. The topic is about the wall insulation dilemma between to spend money to make the insulation thicker versus to remodel and change the size of the windows on that wall. For this problem, I will show the calculation and the solution steps to remodel and change the size of the windows on that wall, because this much more saving energy and money for the family. Next, we will be solving the problems by assuming x equals to the thickness of the wall's insulation, while the variable of y means the surface area of the windows. By using the equation of the Fourier's law of heat, which is Qxy equals to 200 over x plus 15y squared, we will observe that x is defined as x increase, the fraction will be decreased. This means the total heat loss drops, while the y square means that small increase of y will rapidly accelerate the heat loss. So, by using the partial differentiation, we need to use the method because it involves both x and y variables. The first step we need to use is to find how sensitive the house is to insulation. The first step is we need to calculate the dq over dx, and then we will get the answer is negative 200 over x squared. Next, we will continue to calculate the dq over dy, which will be, the answer is the dy. Then we will assume or give the value to x and y, and then we just need to substitute the values into the partial differentiation that we write before, and then we will get the answer is negative 5000 volt over m for the dx, while the dy we will get 60 volts over m squared. Then we will observe that negative signs means higher insulation, the decrease the heat loss, while the positive sun gives the window size increase, then the heat loss will be increased. Based on the data driver recommendations, I will suggest 2 recommendations for the family. The first one is to invest in wall insulation immediately. Adding just 5 cm more of insulation will drastically stabilize the home's climate based on the calculation steps that I just did before. And next, the second recommendation is the cap window modifications. If the family plan to remodel for aesthetics, they must avoid expanding the window surface area unless they are willing to purchase expensive multi-glass thermal glass to counteract the positive derivative. I think that is all for my part. Next, I will pass to the next session.
Now let's move on to problem 2, which applies multiplies integral to solve a real-life problem. During hot afternoon, the sun continuously shines on the roof of a house. As shown in the illustration, solar heat is absorbed by the roof and transferred into the house. This causes the indoor temperature to rise, making the room less comfortable and increase the need for air conditioning. Many families ask how much total heat enters the house through the roof. To answer this question, we use mathematics. Instead of measuring the heat at just one point, we calculate the total heat entering the entire roof surface using a double integral. To model this situation, we assume the heat intensity over the roof is given by Qxy equals to 150 plus 5x plus 3y. Here, Qxy represents the heat flux measured in watts per square meter. The variables x and y represent the position on the roof. The roof has dimensions of 4 meters in the x direction and 6 meters in the y direction. So our boundaries are 0 equal less than equal x and less than equal 4, and for the y, 0 less than equal y and less than and equal 6. As shown in the graph, the shaded rectangle represents the entire roof area where we want to calculate the total heat entering. To find the total heat, we use the double integral Qxy dA. After substituting the heat function and the roof dimension, we obtain double integral from 0 to 4 and 0 to 6, 150 plus 5x plus 3y dy dx. This equation sets up the calculation for total heat entering the roof. At this point, I will hand over to presenter who will perform the integration step by step and explain what the final result means for reducing heat inside the house.
Now that we have established the mathematical model, I'll solve the double integral to calculate the total heat entering the roof. The integral is given by this equation. We integrate each term separately and we got 150y plus 5xy plus 3 over 2y squared. Next, we substitute the limits y equals to 6 and y equals to 0. Evaluate when y equals to 6. We got 150 multiplied by 6 plus 5x multiplied by 6 plus 3 over 2 multiplied by x squared. We got 1954 plus 30x. When y equals to 0, the integral is given by 0. After evaluating the inner integral, we simplify the expression to 155 plus 30x leaving only one variable to integrate. Moving on to the next step, we integrate Q equals to integrate in 0 to 4, 954 plus 30x dx. We integrate term by term and we got 954x plus 15x squared. By applying the limits, by substitute x equals to 4, we got 954 multiplied by 4 plus 15 multiplied by 4 squared. We got 4056. Since the heat flux is measured in watts per square meter and we've integrated over the roof area, therefore the total heat entering the roof is 4056 watts. This result means that approximately 4056 joules of heat energy enter the house every second through the roof during these conditions. This continuous heat gain causes the indoor temperature to rise, making the house less comfortable and increasing the need for cooling systems such as fans or air conditioners.
Over the last 12 minutes, our group has taken you on a journey out of physics lab and directly into the heart of a modern household. We've shown you that the advancement we learn in class isn't just lines on chalkboard. It is a powerful functional toolkit for optimizing everyday life. Let's recap what we accomplished today by looking at how our team used this mathematical principle. First, partial differentiation. As Hazwani demonstrated, when a family faces a complex multi-variable dilemma like balancing wall insulation against window surfaces, partial differentiation acts as our diagnostic tool. It isolated the variables to show us exactly which factor is the most sensitive change agent. It answered the crucial question: where should this family spend their money first to get the highest impact? Second, multiple integrals. As Alia and Frina demonstrate, when a problem spreads out across a physical space like solar heat pounding an entire roof area, algebra simply fails because conditions change across the surface. Double integration allows us to aggregate all of those moving parts and variable heat intensities into a single concrete actionable number, which is 4056 watts. It answers the question: exactly how big of an energy load is this family dealing with? Ultimately, math bridges the gap between raw physics theory and practical family challenges. By looking at the home through the lens of physicists, we can replace domestic guesswork with absolute data-driven certainty. This allows families to make smart choices that save money, conserve energy, and live more sustainably. That concludes our presentation. Thank you very much.